Well, good morning, everybody.
Good morning.
I have printed out the roll sheet, okay, sort of the way I do it. All I need you to do here is find your name. It's divided in two halves. We've got the first section, the 8 o'clock lab, and the second section. So if you don't see your name at the top in alphabetical order, look down. Right? Just go here, and you don't have to initial or sign your weight in blood or anything like that. Just check mark, right? I was here. Fill it out for last week for me, please. And then, fill it out today. No fair filling it out ahead of time, unless you have a TARDIS and a bow tie, then you're all right. But we'll just do roll like this. I only do this for like the first 3 weeks. After that, I don't care anymore. And then if your name isn't on here, there's a big problem, right? Because these are the officially enrolled students as of this morning, right? And so if you're not enrolled, I really need to know about it, okay? So go ahead, send that around, and try to make sure that everybody gets it. Okay. I was confusing you with the other lab, so I don't need to worry about that. I went over this, right? Sort of yes. Broad details. What I really want to do today is do physics, get into this in a big way, get you working with each other and trying things with each other, so on and so forth. So just, I'm going to put it in the same spot that I had it before, okay? And it's this, what did I call this? Toolbox. This is the toolbox, right? And we don't want to reach for our tools until we know exactly what it is we're doing, or at least have some good idea about what we're doing. And like every tool in a toolbox, there's specific uses. And I want to just point out a couple things to you about these tools. If you have no idea what the time is, and you don't care to know the time, how long it takes to do something, is there one of these that's jumping out at you as a good one to use? The last one, why? There's no time in it, right? Okay. So we need to be clever and think about what the tools can do for us, right? In the context of the problems that we have. Now, I'm going to throw a problem on the screen, okay? And of course, everybody's going to want to write down the question. Again, it's going to be on YouTube. It's going to show up on Dropbox. I'd much rather have you right now start engaging with the material and doing it, right? Because you're going to hit your homework later in chapter 2. You're going to say, I don't know what to do. I want you to know what to do because you've done it here in class. So right now, I know you're kind of all reading and you haven't heard a word I said in 30 seconds. I want you to turn to each other and we're going to do the visualize step. I'm going to let you try it first and then I'm going to show you the way I do it. So I want you to visualize with each other. And this could be a discussion of what you're seeing in your mind. But try to make a list or identify what you know. Like try to line up the numbers in this problem with things from the toolbox, right? And what you don't know. Try to think of all the possible things that you could identify. So I just want you to turn to each other right now for a couple minutes. What do you know and what do you not know about this problem? Go.
And then you also have, that's the initial velocity, but you also have a final velocity of 0 because you Can we start it? Why do you have Ed reading up there? Why do you have water safety data for Ed? Go ahead.
Gotta have sources.
Because if it's
What'd you come up with? What's the 27? Is it an initial velocity or a final velocity? How do you know it's initial? That's where it started, and it comes to a stop. So, well, they didn't give me the final velocity.
So it would be 0.
It's implied, right? Because as it comes to a stop, we say that means 0. All right, so you got to read between the lines, right? Infer some numbers sometimes. What's the 3.1?
That's
How long it takes. You'll notice that we don't have sort of a t initial and t final. It's because t initial is almost always assumed to be 0. Okay? So we usually drop the delta t's until we actually need them, and then we'll confuse you by introducing the delta t's. Okay, so good. You're getting some idea kind of how to read the problem. Maybe you're still having some anxiety over word problems, right? Because word problems were always the horrible thing in math, right? My advice is get over that because physics is nothing but endless word problems. So, right? But again, we're here to try and help you get over those kinds of things. So science and engineering is nothing if not systematic, right? We try to approach things with a common method, okay? And although that method seems to be different, like every single problem, it isn't. We're trying to do similar things over and over again because we know that if we do that, eventually we'll learn how to do it right. So here is my symptomatic method whenever I'm encountering something, especially if I know what my toolbox already looks like. So in the language of physics, this toolbox is for one-dimensional motion with constant acceleration. Those are the limitations. My acceleration has to stay the same, otherwise this isn't going to work. Since I have a problem, okay, where I'm finding the acceleration, we're going to assume that it doesn't change. Is that a good or a bad assumption for bad? Does the amount that your car is slowing down by change as you apply the brakes? Yeah, it kind of like gets more and more the slower you go. Your brakes become more effective. However, over the entire car stopping distance, the differences are minimal. And so you can still get useful information out of a simplification like this. At least physicists are okay with that. Engineers tend to not be. My list of what I know and what I don't know comes straight out of my tools. In other words, I'm going to just march through my tools and see all the possible kinds of information I can get. So my list is in the order of the toolbox. I can either know or not know a final velocity. I can either know or not know an initial velocity. What comes next in that first equation? Acceleration. Then time. Okay, to the second equation. What's something I could know or not know? Delta x. And then V naught. I've already got V naught in my list, right? And T, do I already have that in my list?
Yes.
Do I know a half? I know half. You got to take comfort where you can get it, right? Okay. Do I know? Can I know or not? I already got that in my list, right?
Yes.
T.
Yes.
V. V naught.
Yes.
2.
Yes.
A. Delta x. Okay. So this is the complete list of things I could know or I could not know. And now I'm going to go ahead and try to figure out where these numbers go. Where do I put the 27?
The knot.
V naught, 27 meters per second. Where do I put the 3.1? Time. And the implied 0 when it comes to a stop? Go ahead and stick that in final. Sometimes what I do is I go down my list and go, well, was I given that? Or was I given this? Was I given, right? I sort of check all these things. So like, was I given the acceleration? No. What? And I put a question mark there. I don't leave it blank because that tells me that I actually checked. Like I thought about it, right? Now, I might have done it wrong, okay? But at least I have a reminder there that I did go through that process. And then what about distance? Was I given any indication of how far this car went?
No.
No, again, so I'm going to put a question mark. Okay, so this is one method of visualizing. I'll be teaching you lots of methods this semester. Some of them are going to involve pictures. Others are going to involve lists. You may have started by just sort of closing your eyes and maybe imagining coming to a stop. These are all visualization methods. When it comes to problem solving, we do need to have something that we can sink our teeth into, right? And so if you're in that stage of, I just don't know where to start, you're sitting there all alone at 1 o'clock in the morning with your energy drink, right? Start with making lists. Just try it. Sometimes it's enough for your brain to just start getting traction on these things. All right. So that's first step of problem solving method. These aren't really a checklist to go down. It's more of a process that you can start and then get one somewhere, and you may have to go back again and do visualization again or flesh it out some more as you learn stuff. Try to be a little bit flexible with the process. But what comes after visualization in the method? Do you remember? Strategize. So this is where we're going to come up with a plan. Okay? So what I want you to do right now with your neighbors is, considering what we know and what we don't know, turn to each other and have a discussion on what tool you are going to use. What are you looking for in just part A? Just worry about part A, okay? What tool are you going to use and how are you going to do it? Don't do it, but talk about how you're going to do it. Go. Alright, what'd you come up with?
Use the first one, use the first one.
Use the first equation to find
acceleration.
To find acceleration. Okay, that right there is a plan. Now, exactly how much algebra have we done up to this point? Zero. What have we done up to this point? Physics. Right? Physics is the art of conceptualizing what's going on, writing it down in a way that allows us to manipulate and solve, right? Physics never starts with the math. It just doesn't. It starts with trying to understand the physical parameters and then turning to the tools and then doing it. So, since you're beginners, I really recommend, this is going to save you time later, I really recommend that you write down your plans. Just as you're solving the problem, you're making your list or whatever visualization you've done, when you come up with a plan, write it down. If you don't want to write it, like I don't like writing because my handwriting's horrible and I can't read it anyway, I'll say it out loud. I try not to make sure there's anybody in the room because they, don't. But I'll say, I'm going to use the first equation and I'm going to solve it for A. That sets the plan, right? Now, the nice thing about writing it down is that later on when you're confused and you're drowning in the algebra jungle and you can't remember what it is you were trying to do, you'll have the plan right there. Oh, that's right, I was trying to solve for acceleration. Right? Because there will be moments in this class, more or less every day, where you're just like, what am I doing? You get so far into it that you can't remember where you were going. So having that written out. Now, eventually, will you get to the point where you don't have to write down your plan? Sure. Right? But again, because you're new and you're starting this, right? Just taking that extra 10 to 15 seconds to write out your plan can help you later, right? As in case you get lost, come back to it. I'm not going to write it down on the screen because my real estate's limited and my handwriting's really bad. But the plan is we're going to use the first equation and we're going to solve it for A. Sidebar here. Your book, I think, has 6 of these that they refer to as the equations for one-dimensional motion or something like that, okay? I've never found a situation that I needed more than these 3, okay? So this is why I refer to these as the 3 equations of kinematics. I can get the other 3 by combining these in various forms, okay? And those other 3 equations, while nice to have around, aren't typically useful very often, right? So again, lists of 3 about the most I can do, right? So that's why I only keep 3 in my box, my toolbox. All right, and I say that, right, because if you're looking at Google or Chegg or whatever you're using to help you with your homework, you will sometimes see equations come out of nowhere, right? You'll be like, where did they get that, right? Well, it's possible that they had a different list they were working off or something. Try not to think of physics as just finding the right equation, right? It's more than that. All right, so I'm going to go ahead and make sure that I copy my tool down correctly. It's another problem that I have. And now that I've got a plan, what's the next step?
Do it.
This is the do it step. And this is where you can take a break from the physics because what you are about to do is math, right? You're going to use the rules of mathematics to solve for what you're looking for, right? Don't break the rules, otherwise you're breaking the laws of the physical universe. Okay, and this is typically in this class where I go really fast. Sometimes I don't even show you my step. Actually, all the time I don't show you my steps because this isn't a math class, right? And so try not to get hung up on the fact that I'm just going to go ahead and write down this. I've done a lot of math in my life, right? And I can do lots and lots of steps in my head. Not only that, I looked at my notes earlier this morning. Right? Okay? If I tried to teach this the instant I walked in this morning, I would look like an idiot. Right? Okay? Your teachers look like they know what they're doing only because we have notes. So I do skip a lot of math steps in here. Right? I didn't subtract from both sides and then divide on both. I mean, I did that, but I didn't write any of that down. If you do that on an exam, am I going to kill you? No. Right? You want to skip steps? That's fine. But I cannot give you the benefit of the doubt if I can't see an orderly progression of your work. And by that I mean, I'm looking not only whether or not you got it right or wrong, but if you got it wrong, I want to see why. And if it looks like you were doing like physics, awesome, physics, math, and then maybe you were showing me what you were trying to do and you forgot to carry that minus sign over, I am inclined to go, you know what, that's a stupid math mistake, right? This person knows their physics. They did a little tiny stupid math mistake. I'm going to give them credit for that, right? And I'll do that on an exam, right? So the more you can show me, the better I can help you, right? See where you're at and what you understand. If you're skipping big steps and it goes wrong, I'm like, okay, they didn't show me what was going on. What's wrong? So, be as verbose as you can. Does everybody get the roll sheet? All right. So, now that I've got that solved for my acceleration, I'm going to go ahead and chuck in my numbers. You're welcome to put the numbers in first. That's fine. But I will always work in symbols as far as I can, for reasons that will become apparent later. All right, 27, right, meters per second, minus, nope, try again, Mr. Balo, final, minus initial all over the time. Now, why didn't I put my units in?
Because you kind of know the units.
Because I'm awesome.
Yeah.
You can, and you might want to, especially if you're kind of new to units. For me, it's visual clutter to have all the units in there, right? I can't see what I'm supposed to be doing in my calculator if the units are written in. But here's how you get away with not writing units in your intermediate steps. Make sure that every unit you use is a metric unit, a standard unit. In other words, if you're talking about speed, what units are you going to use? Meters per second. So they give you something in miles per hour or kilometers per hour. What are you going to do? You can convert it. Okay? Acceleration is always going to be in meters per second squared. If you don't know why it's meters per second squared, you need to read. Right? Again, it's not something I covered. Time will always be in what? Minutes, hours, eons? Seconds. This is what I call standard units in equals standard units out. If you're putting speeds in meters per second, accelerations in meters per second squared, time in seconds, distance in meters, if you're using the standard metric units for these things, the equations, the tools, are already calibrated for those. They are what we say it's dimensionally consistent. Okay? In other words, if you're solving for a velocity, you're going to do a velocity plus a velocity. And acceleration times the time has the same units as velocity. So, if you're doing standard units in, you will get standard units out. In other words, I'm solving for acceleration. And since every number I put in was in the SI unit system, I'm guaranteed to get the units of acceleration in the SI system. So that's what I do. You don't have to do that. Again, you could put 0 meters per second minus 27 meters per second, which is great, right? Because it's showing you that you're subtracting an apple from an apple, right? If you were doing 0 meters per second minus 27 meters, can you subtract a speed and a distance? No, that doesn't make physical sense. So having those units in there can really kind of help you check along the way to see if you've done it right. But for me, again, I look at that and I go, right? It's too much for me to see all of that. My brain gets confused really fast. Okay, did anybody do this in their calculator and get an answer?
Yeah.
What is it?
A negative 8.70967.
8.7, okay. Meters per second squared. I'm going to put a box around it because it's my final answer, right? And I'm all done. I can go home now? What's the last step?
Just check.
Check it. We've got to check our answers. Now, this is what's going to happen. This is what your check it step is going to become because of the online homework system. You're going to get a number. You're going to type it in the box. If it goes red, you're going to cry. If it goes green, you're going to be like, I'm done. Right? And you're going to move on. Exams don't have green or red boxes. Life doesn't have green or red boxes, right? The real world, when you get it wrong, is pretty brutal sometimes, right? So having mechanisms to check independent of the green or red box, really important. What's the first thing I want to check in this answer?
If acceleration works.
No. What the heck is the minus sign doing there? You need to demand, of your answers, you need to pin them to the wall and say, what are you doing? Why are you negative? Why is it negative?
Because you're
Slowing down. It's coming to a stop. Should the acceleration be negative?
Yes.
Better be, because we said the initial velocity was positive. Whatever direction that is, we said it was the positive direction. So if it's coming to a stop, the acceleration has to be the other way, doesn't it? Okay, that seems reasonable, doesn't it? What about the number, 8.7? Is there a way to check that? Please don't say plug it back in. Do this with physics. Well, yeah, but we already did the negative sign. I'm talking about like the number, 8.7.
So it's negative 8.7 meters per second squared, and it's only 3 seconds. So
So that means every second that goes by, 8.7 meters per second is the change in velocity. What physicists will do is we will simplify this a lot. We'll say 8.7, that's close to 10. Right? And it did it for 3 seconds. So to get to 0 after 3 seconds with an acceleration of minus 10, what do you have to do? Start where? If I'm going to get to 0 in 3 seconds, and every second it's going to change by 10.
So you start at 30?
Got to start near 30, right? Because I'm going to go from 30 to 20. There's 1 second. And the second, I'm going to go from 20 to 10, right? Because it's slowing down by about 10. And then in the last second, I'm going to go to 0. So my acceleration should be about negative 10, right? Is 8.7 about negative 10?
Yeah.
Close enough, right? Because it's really 27, not 30, and it's 3.1 instead of 3, right? But it's within the ballpark, right? And there's where that order of magnitude calculation comes from. And we combined order of magnitude with the concept of acceleration, the amount that your speed changes every time. So I'm starting to feel better about the result that I've got here. I also have the advantage I've been using this example for like 12 years, so nobody's told me it's wrong yet. All right. What I want you to do right now is turn to each other and do the visualize and strategize steps for part B. Okay? Go ahead, right now. How are you doing right now? Like mentally, emotionally?
Good.
Pretty good.
Exhausted? My brain's kind of starting to fizz a little bit, right? Okay. Are you feeling overwhelmed?
No.
No? Are you feeling like there's a little bit of hope? Like you could maybe do this? Okay, let me tell you what's going to happen. You're going to go home, you're going to try it, you're going to fail. Guarantee it. Not because I doubt you, but because this is physics and this is what happens. Okay? It just happens this way. And so my recommendation to you is try to fail together. What do I mean by that? Work with somebody, right? Because you can generate more ideas faster by bouncing it off somebody else. Now, it doesn't have to be face-to-face. It can be through the snaptograms or whatever, right? Okay? But it just have somebody to bounce ideas off. Your dog and your cat don't work. They're nice, but they can do quantum mechanics. They can't do this. So, I'm just warning you. You're going to get frustrated, and there's going to be, you get emails all the time. Mr. Bailo, I can do it in class, but then I go home, I try it myself, I can't do it, I'm stupid. No, right? You just need practice. That's really what it is. Okay? Practice, practice. And I'm up here, of course, making it look easy. Have you seen those commercials where it says, they're trying to sell you a car, right? And it doesn't matter what the car is, it could be a minivan, right? And they're taking it around mountain roads and drifting it around the corners and all that kind of stuff, right? Okay? In this effort of, oh, I want a car that does that, right? Okay? What does it say at the bottom of the screen in the fine print? Yeah, professional driver, period. No. Professional driver on closed course, period. Do not attempt, period, right? Okay? I'm a professional driver, right? I do this a lot. This is my job, right? So I come up here and I go, oh, right? And then you go home and you try your first drift around the corner and you're just going to end up in a mangled heap. That's okay. Learn from it, right? Write down, where am I stuck? Why am I having trouble? These are the kinds of questions that if you bring those to me, I can go, okay, well, what did you try? What did you do? We can fix it, right? So just be prepared for that. Don't want you to feel gypped, okay? Oh, no. Come back. Stupid button. Okay, so this is the list I came up with. How does it compare with the list you came up with? Hopefully you just erased the question mark and stuck with it, right? Okay. One of the other things I do in my strategy step is I often draw a circle around the thing I'm looking for. Okay? Even though I might write down or say out loud what my plan is, I draw a circle. So what did you come up for strategy in terms of like which tool to use and what?
Second one.
The second one. Okay, so what's good about the second one?
You don't have to do any moving around because
No algebra then, right? Okay. The second one's already solved for me, isn't it? Already got the position in. Do we know this?
Yes.
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 Yes. Yes.
Right? Done.
Why not?
Now, could you use the third one?
Sure.
Yes. Do we know what the final speed is?
Yes. No.
That's okay, right? Because it's the only thing we don't know. But it does mean I have to do some algebra. If I can avoid math, I will. So, the plan, the strategy, again, I'm going for delta x. Colors are optional, by the way. I'm going to use the second equation, second kinematic equation. I'm going to solve it for delta x. Done. So now I can just plug in some numbers. Again, since I'm putting standard units in, I'll get standard units out. That means I should get meters out of this. I have a 27 times a 3.1 plus a 1/2 times a negative 8.7 times a 3.1, and I usually like to forget the squared myself. Anybody get this number? 41.9 meters. So close to 42, the perfect number, the answer to everything. Right? Okay. How do we check this one?
So the change in distance is almost 42 meters.
If you try the check that I just showed you, your brain's probably going to shut down or get a cramp or something. Because distance and time and acceleration are not directly related to each other the way they are in the first equation. There's a quadratic hiding in here, isn't there? Quadratic in t. And our brains really don't like quadratic relationships, parabolic relationships. So kind of doing that brute force physics doesn't necessarily work. And so as a second defense, you can try to see if your answer is reasonable by relating it to things you already know. 42 meters, close enough to 50 for me. And is there something that I'm familiar with that's about 50 meters? I'm thinking about sports. An American football field is how many yards? 100 yards. And a meter is about a yard-ish. They differ by a few inches, but it's close enough. So, could a car going 60 miles an hour, 27 meters per second, come to a complete stop in the distance between the end zone and the 50-yard line.
Yes.
That seems reasonable to me. That doesn't seem out of the ordinary to me, right? Now, if we had gotten an answer that was like 150 meters, that's 1.5 football fields, right? Like, something's wrong here, right? And so there are times that you can go back on your experience to determine whether or not your answer is even reasonable or not. That's a decent check. You're in a lot of trouble when you get to 4B and you have no intuition for anything. But it's one way to do it. What's another, perhaps more engineering way to do this in terms of making sure you got the right answer that isn't sort of fuzzy the way we physicists do it? Test it. Well, okay, going straight for the engineering. Yeah, just go out and do the experiment.
Just drive the car.
Now, there's another way to be more precise in the check. We've already talked about how to
Plug
do
it in.
Yeah, but plug it in how? Do it differently. We had another way of doing it, didn't we? And so we can independently verify our result by doing a different tool. We do have to do some math here. But now, if you get the same answer or really close to the same answer, I'll be doing it right. Is there a question?
Yeah. So do you mind explaining to me how you got the acceleration 8.7?
So that came from our earlier problem. That one right there. It was part A.
Thank you.
Yeah. I just carried it over because we're in the same car. Nothing changed. Okay. Still doing all right? Okay, let's see if we can break you. I want to give you about, 4 to 5 minutes here. Okay? And I want you again to, with each other right now, set this problem up, visualize, strategize, and don't be surprised if you start running into trouble. Okay, go. We do it by doing the other. Yeah, 12. Using the third one instead. Go solve the problem again. You get 41.8.
I want to say
Draw pictures, make lists. I can tell just by looking at it from this far away.
Don't mind if I just take a picture of the question.
Sure. It is going to be on graph.
This is just a way to test myself. Thank you. I like to test myself every time I practice a problem. One time, we got acceleration, initial velocity, we got
This one.
Yeah, we pretty much have enough time. The first
So then,
Oh no, it slams on the crate. Hey! I've let you suffer long enough. So this is the compilation of your body language for the last 4 minutes. Are you ready? Okay. This is how you start. As you first started kind of shy because you didn't want to talk to anybody. And then you got into your group, right? You started talking. You were like, right? Because you were like, ah. And then it went to, right? You went from, oh, I can do this to, what? Like, what's happening here? I have so many questions now. What do I do? It's by design, okay? What did you come up with? Where did you get stuck? What are the questions that you have? What's that?
2 cars.
There's 2 cars. So did you come up with a solution for that? 2 lists.
So where I got stuck was figuring out time, just because it
Yeah.
didn't say it.
It doesn't have time in it, right? So it's like, what do I do? Where else did you get stuck?
Since there are 2 cars colliding, should we wait for them to slam into each other and move them just the first one forward?
Like, so what happens? So like, I've got a difference in distances to begin with. I've got cars slamming into each other. When do I stop? Is it the instant they slam into each other, or do they come to a sliding halt in the road? Right? It's a good question.
You want the distance to be 0.
We want when they collide, the distance is 0.
Yeah.
But is 10 meters the distance both cars traveled before they collided? No.
one of them.
Stop right there. Some of you are going, well, yeah, it is. No! 10 meters is what they're separated by. But they both drive some distance before they collide.
Isn't that irrelevant?
No?
Don't we just care about the
The first car is like from the first problem, right? So it
Yeah.
takes 41.9 meters to come to a complete stop.
Complete stop.
But the car behind it is not going to hit it once it comes to a complete stop. It's going to hit it once it catches up to the speed.
Right, so we can't count on that 41.9 meters, right? The front car does not, front car, as a matter of fact, never, back car never changes its speed. Front car is slowing down. This is going to happen long before the front car comes to a stop. 10 meters at 27 meters per second, right? Okay. But we can't just do the 10 meters for 27 meters per second because the front car is changing its speed. It doesn't stay at 27, does it? Okay, so we're going to trust the method. We're going to trust the method. We're going to try and figure this out. So, visualization. Somebody mentioned we've got 2 cars, so that means 2 lists. Write down information for the objects you have in the problem. So, we'll have car number 1, and we will have car number 2. Now, I am kind of a visual person. I kind of like to have pictures. So, I'm going to draw a picture. This is kind of like drone's eye view, bird's eye view, helicopter's eye view, looking down on the scene, right? So, I've got 2 cars. They start 10 meters apart from each other. But eventually, they're going to move to a point where they bang into each other, right? So now I just need to make sure I keep my numbering straight in my head for my lists and my picture. So I'm going to call the car in front, I'm going to call it car number 1. I'm going to call the car in back car number 2. So at the end, they should look like that, right? Again, the picture is a way for me to kind of anchor all the information I've got in the problem. Sometimes I don't even make lists. Sometimes I just write the numbers attached to the box in my diagram, right? Okay, so kind of depends on how I'm feeling that day or whatever. I'll do lists because I've been doing that today. So what do we know about car number 1? Oh, what can we know or not know about car number 1? Where did that list come from?
The last list.
These are the tools I'm working with. So they come from, is that list going to be the same for all of chapter 2? Okay. For car number 1, do I know what's car number 1? Car number 1 is the one that slams on its brakes, right? So do I know how fast the car is going when the 2 cars collide? No. Problem doesn't tell me anything about how fast car number 1 is going when the collision happens. Is it 0? No. It doesn't say the front car comes to a stop.
27 meters per second, because at the point of collision, it never slowed down.
But this is the car in front, right? The one that slams on its brakes. So yeah, so as soon as it slams on its brake, it's starting to change its speed, right? But we don't know what speed it's going. Be really careful about assuming things, right? Because those can lead you astray. Okay, do we know, that's supposed to be a V naught, by the way. Do we know the initial speed of car number 1? Yeah, it was 27. Okay. Do we know the acceleration of car number 1? I wonder where they got that number. Okay. Okay. Do we know how much time elapses before the collision happens? Yep. Do we know how far car number 1 has gone before the collision happens? No. And now, this is kind of where the panic begins to set in. Because there's an awful lot of question marks. Right? All right, but let's trust the process. Let's trust that this is going to see us through, and maybe when we get more stuff written down, maybe something will snap in our brains. Car number 2. What's car number 2's final velocity? 27. Huh? How fast is car number 2 going when it collides with car number 1? Why? It didn't change its speed, right? What was car number 2's initial velocity? 7. Car number 2's acceleration? 0. Why is it 0? Never changed its speed, right? Okay, so 0. Do we know how much time elapses?
No.
Yep. Do we know how far it went before it collided? Delta x is the distance between when we start paying attention, right as the front car slams its brakes, and the total distance the cars travel before they collide. It is not the same as the distance between the cars.
So then would it be delta x of the car 1 minus delta x?
You're close, but not quite there. You're hovering around the right idea.
The same for both, right?
What is the same for both of these cars?
Initial velocity.
Initial velocity is the same. What else? Time. Time has to be the same. Because we're going to start the stopwatch at the same time, right?
Delta X.
No. Delta X is not the same.
It is
Because if car number 1 goes 50 meters before the collision happens, how far does car number 2 go?
60.
60 meters. Is that what you were trying to say? Yeah. Okay. So we've got to figure out how to capture that idea where one car goes a delta x, but the next car is going a delta x plus 10. To capture that in the language of these tools. And the way we're going to do it is we're going to remember that delta x means something. What does delta x mean? It's a final minus initial, isn't it? And we can write that down for both of these cars. But they are going to disagree on one thing. What's the same for both cars? The final or initial position? The final. They collide, right? Whatever that location is, it's got to be the same location. That's how the boom, right? But what's different? Where they start. Because one of them starting 10 meters different from the other. So we have to make a decision now. Where are we going to put 0? We're going to put 0 where car number 1 is, or where car number 2 is.
2.
How many of you want to put it on car number 2? How many of you want to put it on car number 1? How many of you are totally lost? Right, good. Thank you. Thank you. Right, okay. The answer is it doesn't matter. As long as you are consistent with your choice. I'm going to do it both ways. Let's start. I know most of you said car number 2. I'm not going to do that. I want you to be uncomfortable. Too late, Mr. Bale. I'm already uncomfortable. I'm going to put 0 on car number 1. So I'm going to say that's 0. And this means now that when I go to write down the final and initial positions of car number 1, I don't know what its final position is. But what is its initial position now? 0. Why is it 0? Because I said so. Right? I put 0 at car number 1. Okay. Now that I've made that choice, all choices have consequences, good and bad, and indifferent.
It's -10.
Ah!
I just take
Should have been over here. Sorry. Got my thing. This one is I don't know, and this one is 0, right? Okay, now, sorry. What do I write down for the initial position of car number 2? Say it out loud. -10. Why -10? It's to the left of 0. And we said that 27 positive was that way because I drew my diagram that way, right? I have to put down -10 because the car starts behind my 0 point. Okay, for those of you that wanted to put 0 at car number 2. So there's my car number 1 and 2, right? If we put 0 at car number 2, then what will be the initial position of car number 2? 0. And what will be the initial position of car number 1? Be very careful. Positive 10. That's why it doesn't matter what you choose. The math will sort itself out anyway. But you have to be careful with your choice. Make a choice. And then the word I use is be consistent with your choice. I don't care where you put 0. Put 0 on the moon. But now you have to make those corrections. Orbital dynamics. Don't put 0 on the moon. Okay. So, I'll stick with my original 0 here on the screen. Okay. 0 at car number 1. Okay. What are we looking for? I've already forgotten because I didn't circle it. We are looking for time. And you already told me the time has to be the same for both vehicles, right? So I'm after time. I want a strategy that gets me time that doesn't... What do I not want to have? In other words, where are all my question marks? Final velocity of car number 1.
And X. Each position.
Final position of the 2 cars. Car number 2. If we wrote down equation number 1 for car number 2, like I'm desperate now, I'm just going to flail around with some equations and see what happens. What do I write down for car number 2? 27 equals 27 plus 0. True, but useless. That's how you know that it's math. What about the third one? 27 squared equals 27 squared plus... Still true. Only more complicated now. Because now you have plus or minus. So, for car number 2, are the first and the third going to help me at all? No. So what does that leave? Second one, better help. So part of my strategy is, okay, I got to use the second equation for car number 2. All right, what about car number 1? What's wrong with the first one? Final velocity and time. Both unknown. That's too many unknowns in one equation. I'm good with like one unknown in one equation, right? But to have 2 unknowns in one equation, that's a bad thing. What's wrong with number 3?
2 unknowns.
Same problem, right? Which suggests I could use 1 and 3 together somehow, but now my brain is shut down.
Also, T is not even in that.
Yeah, T's not in that one, so it's not going to help me. So what does that leave us? Number 2. But number 2 has 2 unknowns also, right?
Where's your X finals are the same?
But I already know I want T. I'm looking for it, right? So I want to leave that one in somewhere. Okay, it's an unknown that I want, so I'm going to leave it in there. But maybe because delta X has a relationship, maybe I can exploit that. Right?
Can we just factor for T?
Yes, we're going to do that, but not quite yet. You're looking ahead, which is great. All right, so what is my strategy? My strategy is write down the second equation for car number 1. Use that one. And the second equation for car number 2. And then let's see what we can eliminate. Extra baggage that isn't going to be necessary. Car number 1. Let's see. Can't do much with that red equation there, can I? I mean, I can plug stuff in, numbers in, but I'm not going to do that yet. No, I can't do much with the red equation. But what about the blue equation? What is there a term that I can just get rid of here in the second equation?
A.
The 1/2 AT squared. Why can I get rid of the 1/2 AT squared? Because the acceleration is equal to 0. So this is kind of a curious notation that I've seen various physicists over the years use. We draw an arrow through the term, which means we're getting rid of it. And then if we're being really nice, we'll write down y. Otherwise we won't, and we'll just let the reader assume that you know what we're doing. Right? But I like leaving that little note that says, I got rid of this term because if I plug this 0 value in, right, it's going to wipe it out. I don't want to carry it around as extra baggage. Okay. Again, let's be really careful over here. What did I do with the delta x? I wrote it out, right? Whoops. I'm going to go same thing over here. Okay. Is the strategy becoming apparent now? What do we need to do now? Set the. How do we set them equal to each other? Solve for final position for both of them, and substitute it in the other, or set them equal. Or notice that we had to do kind of a combination of visualization, strategize, and a little bit of do it, right? To be able to work our way kind of towards the final strategy. And that's okay. This method is designed to be malleable like that. But I hope that one of the things you take away today from this class is that you've broken the habit of reaching for the equations first. Come up with a method that works for you. Doesn't have to be mine, right? But come up with a method that works for you that gets you thinking about what the numbers mean, what are the physical parameters of the system, how do I organize my information, and then come up with a plan. What do I have and where do I want to be? And how then do the equations fit into that? If you can do that, if you can learn that early in this course, because to be successful in this course, at some point you're going to learn that. Do it early. You're going to save yourself so much time this semester. All right. Maybe at this point I'll just toss some numbers in because it'll be easier. I don't know what the final x is for car number 1. But I do know the initial position was 0, right? And then it's 27t plus 1/2 minus 8.7t squared. All right. Over here in the blue, this one is going to be a minus. What do I put in for the initial position of car number 2? -10. It's a negative of a negative, right? And then 27 times t. The blue one looks nicer. I'm going to deal with that one first. This is going to be 27t minus 10, isn't it? So I'm doing algebra now, and I'm going to be going fast. That was a negative and a negative, which became a positive, and then to move it to the other side of the equal sign, it picks up a negative. All right, some of you are staring at me like, what the heck math is he doing? Okay, insight into how I dealt with algebra. In this problem right here, we had an x minus a minus 10 equals 27t, right? Okay, so your math teachers probably taught you to write the next line, which would be that. And then how do I solve for x? I've got to get rid of this 10. So to get rid of this 10, what do? We add a negative 10 to both sides, right? And when we do that, it cancels on that side, and I end up with over here that, right? All right. That was too much for my simple brain in high school. Okay? And so I came up with tricks in my mind, shortcuts to get me places. And one of the shortcuts, again, my mind works in visualizations. And so when I see that, in order for me to get x by itself, I move the 10 over. And anytime I move something to the other side of the equal sign, what happens to it?
Changes.
It gets a different sign. Whatever sign it had on that side gets the opposite one on the other. If I'm moving it in a fraction, in other words, dividing or multiplying, right? Then I don't have to worry about the signs. I just got to make sure it ends up in the upstairs or downstairs category. So when I say, I'm moving it on, I go, okay, move it to the other side, and boom, boom, boom. That's what I've done, right? Okay? Rather than think about adding or subtracting to both sides. I'm just moving stuff around. Okay? To me, algebra is very visual. It's about moving puzzle pieces around to get what I want. But again, this isn't a math class, it's a physics class, so I didn't have to tell you any of that. All right, over here in the red, it's going to be 27t minus 4.35t. What the heck just happened right there?
Substitution.
I divided by 2. Because I don't like fractions. Fractions are evil. All right, set these equal to each other or substitute in x, whatever way you want to think about how this is supposed to go. But what I end up with is 27t minus 10 equals 27t minus 4.35t squared. And the panic really starts to set in at this point, doesn't it? Because we're quadratic in t. Oh, but you don't fear quadratics? No? Quadratics are nice? Okay, I'm going to put them all on the test. This one isn't yeah, do it, man, we got this right. And then whoever, what's your name? Kill him. All right. So, it's not quadratic in t, actually. Because what happens?
Because they cancel.
I got them on both sides, right? So that one goes away. And then I end up with algebra in my head. This is going to be 10 over 4.35 square rooted. And when I did that, I got 1.52 seconds. All right. When you are doing your homework and you're confronted with a problem that involves, I believe, a car and a motorcycle, maybe a police officer, and the police officer is going to start trying to catch up and all that kind of stuff, you may want to try a method similar to this one. 2 objects, that sort of stuff. There's a twist in your homework, though.
They're still moving.
They don't start at the same time. Be careful. Yeah, be careful.
Do they still
Okay.
start the same thing?
Yeah. All right. Okay. I've had you do a lot of teach each other today. We haven't done any quizzes. So I don't want to give this as a quiz. But what I do want to do, this is again, are you reading enough? Are you understanding enough, right, about the content that's in there? As of next week, I'm not going to have this. I'm not going to do this exercise anymore. We'll just do straight quizzes, and either you know it or you don't. Okay. But right now, in little groups, check. See if you know the definition of free fall. Go. Help each other out.
A free fall is when moving under only the influence of gravity. So the only force acting with gravity. That's free fall.
Yeah.
Oh, we will in the future. Well, yeah.
All right. By show of hands, how many of you say the answer is D? No? C? Starting to get an insight into my sense of humor. Right? D?
Yeah. We say B.
B? Yeah. And A? All right, good. Okay. So maybe a little bit too easy, right? But it's easy to forget, okay, that when a physicist says an object is in free fall, we're not just being artsy or Englishy, right? We're very specifically trying to communicate that there is one acceleration that matters here. And it's this one. Okay? Yeah, let's be very careful. This is not gravity. Because gravity is a force. What does this have units of? Acceleration. We haven't talked about gravity, I talked about force. We're not going to do that until we get to really chapters 5 and 6. Okay? But it's enough right now for me to tell you that gravity being the thing that accelerates freely falling objects, it always accelerates those objects at the same rate. If you step back and you think about this for a second, that's a little bit amazing, right? Like, it really shouldn't be that way. In other words, if we went out here and I took an elephant and I took a mouse and I dropped them both off the edge, which one would hit the pavement first?
Depends. No, it's the same.
According to Galileo Newton, they should hit at the same time, right? So, I brought with me an elephant and I brought with me a mouse, right? Okay? They differ in their mass, right? One of these is more massive than the other. So I'm going to hold them at exactly the same height. I'm going to drop them, right? And which one's going to hit the ground first?
Air friction.
There's drive.
This says they both accelerate at the same rate.
In a vacuum.
And they have
In a
different
vacuum.
They have different surfaces.
Thanks, paper.
Right? Okay. But was that free fall?
No.
Why not? Air friction, air resistance. There were other forces there besides gravity. Again, I'm not holding you to that because we're going to talk about forces. You're smart. You know what's going on. Okay? So, what I would like to do now to prove to you that gravity accelerates all objects at exactly the same rate is I'm going to suck all the air out of this room.
Do it.
I want you to hold your breath. Okay? Maybe close your eyes because the pressure differential on your eyelids doesn't feel good. Right? Your 8 years. Do that for about an hour and a half because that's how long it'll take to evacuate the air out of the room, and then we'll repeat the experiment. You ready? Okay? But I am going to do magic. You ready? In this room, this very air, this very time, I can make both of these fall at exactly the same rate. Are you ready?
Fancy.
Right? What did I do? I made sure that the air resistance was the same.
You cheated and you taped it.
No tape. No tape. One better.
We will use this pair of tubes containing metal and paper discs to show the effect of eliminating air resistance. This is how the objects fall when the tubes are filled with air.
Exciting?
Oh, yeah.
If we now remove most of the air from the tubes with a vacuum pump and repeat the demonstration, the results change dramatically.
That's quiet. That's a pretty quiet pump.
How are they hitting?
Same.
Exactly the same. This is not CGI. Right? So you get rid of the air resistance, and the only thing you have is gravity, and everything falls at exactly the same rate. Okay? Now, if that bothers you, bigger things, more massive, blah, blah, blah. Bigger things experience more gravity. And you've encountered this idea before. Not the gravity one, but the idea that things change in proportion. Somebody tell me what this is.
Pi.
Pi. I like pi. What's pi?
3.14.
No. It's the ratio of the circumference of a circle to its diameter. Right? By definition. It happens to be, in our universe, 3.141596. Right? Doesn't matter how big the circle is.
No.
So pi is pi for that circle? And that circle?
Sure.
And one as big as the sun? Sure. Little g is exactly the same way. Little g actually comes about by taking a look at the ratio between the force of gravity and an object's mass. Again, we'll get into this later when we get to Newton's laws. But if you've got a bigger mass, what will gravity do to compensate? Apply a bigger force in order to keep the acceleration in free fall exactly the same. I'll do one example of vertical stuff from out of chapter 2 next time, but then I'm going to do the entirety of chapter 3, because really the end of chapter 2 is what we just did, just vertically instead of horizontally. Okay? So you should be able to do all of your homework now in chapter 2. Finish up chapter 2 with one example. Do all of chapter 3 on Wednesday. And then lab on Thursday. Have a great rest of the day.